let's pause the movie when the car comes to point A. Let's wait for a small time for the car to come from point A to some point B. Now, to calculate how much the acceleration is, we need to first be able to visualize the change in the velocity. Can you visualize that just by looking at this picture? Here, let me help you. So at point A, the car's velocity was pointing this way. Now at point B, it has turned and it's pointing in that direction. Therefore, the green arrow mark represents how much the velocity has turned or how much it has changed. So the green arrow mark represents the change in the velocity. We'll call it as delta V. Now we're ready to tinker with the speed of the car and the radius of the circle and see how acceleration depends on them. Let's begin by tinkering with the speed. Let's say we double the speed of the car. What will happen to our change in velocity delta V? Well, first, because the speed is double, the velocity vectors now become double in size. And so immediately you can see that the change in velocity delta V also increases, and I'm guessing it also doubles in size. But we're not here to do guesswork, we can do more than that. Can we compare the new delta V with the previous delta V? Sure, we can just look at the two triangles. If you look at this small triangle, we find that all its angles are exactly equal to the corresponding angles of the big triangle. Which means these two triangles are similar triangles. Their sides must be in the same proportion. But we know this side of the big triangle, which is the new velocity vector, is twice as big as before. Therefore, all the other sides of the new triangle, big triangle, must also be twice as big as before. Therefore, this side, which represents the new change in the velocity, should also be twice as big as before. So yeah, indeed, the change in velocity has also doubled. And at this point, we might say, aha, therefore, the acceleration must also be double, right? Well, remember, acceleration is not just change in velocity, it's change in velocity divided by the time taken for that change. Remember, it's a measure of how quickly the velocity is changing, which means we have to look at the time taken for the car to go from A to B as well. So let's do that. What happens to the time taken when we double the speed of the car? Well, now the car is going twice as fast as before, which means the time it takes should reduce to half as before. Now we can put it all together and see what happens to our acceleration. We have twice the change in velocity in half as much the time, which means you can see the acceleration actually increases 4 times or 2 square times as before. Oof, can you see where that square is coming from? But before we start celebrating, to convince ourselves, let's take one more case. Let's see what happens if we were to now triple the speed of the car. Now would be a good time to actually pause the video and see if you can go through all the chain of thoughts yourselves and arrive at what the new acceleration is going to be. Go ahead, pause the video and give this a try. Okay, so just like before, now that the speed is tripled, which means the velocity vectors also become thrice as big as before. And similarly, the change in velocity will also be thrice as big as before. And I'm sure you can convince yourself of that yourself. Same methods, we can use similar triangles. So delta V becomes thrice as big as before. And what happens to the time taken to go from A to B? Well, now since the speed is tripled, the car goes thrice as fast as before, which means the time it takes will be 1/3 as before. Putting it all together, the acceleration is we have 3 times the change in velocity in 1/3 the time as before, giving us 9 times more acceleration or 3 square times more acceleration. So right in front of your eyes, you can see that the acceleration is proportional to v squared. And where is that square coming from? Well, when we increase the velocity by some amount, not only does the change in velocity increases by that same amount, but we also find that the time taken decreases by that same amount. These two factors combine together to give you that squared. Now let's look at how it depends on the radius. Now let's double the radius of the circle and see what happens to our acceleration. So the radius doubles. Let's now look at what happens when the car goes from A to B over this big circle. And my question to you is, what do you think happens to delta V? Does it increase, decrease, stay the same? Can you visualize it? Can you pause and check? Yourself. All right, because the car is traveling through exactly the same angle as before, what we find is that the velocity vector is also turning by exactly the same angle as before, which means the change in the velocity delta V would be exactly the same as before. So since delta V is not increasing, we can say the change in delta V or increase in delta V is just 1. It increases 1 times. So we can get rid of delta V. We don't have to focus on it because we know delta V is not changing as we increase the radius. But what about the time taken to go from A to B? Well, now since the big radius is twice as big as the small radius, we know that the distance AB will be twice as big as the old distance AB. But remember, our car is moving with the exact same speed as before. We're not changing the speed now, which means the time taken for this car to go from A to B would be twice as much as before. So putting it all together, how does radius affect the acceleration? Well, we have the same change in velocity as before, but it's happening in twice as much time as before, so the acceleration becomes half. Similarly, what happens if we triple the radius? Well, again, as the car travels from A to B, the delta V will be exactly the same. So the increase in delta V, we would say, is 1. But now, since the radius is thrice as much as before, the distance AB that the car has to travel is thrice as much as before. But it's traveling with the same speed, so the time taken would be thrice as much as before. And when we put it all together, we see the effect of tripling the radius on the acceleration is we have the same change in velocity as before, but in thrice as much time as before. And so the acceleration becomes 1/3. And so you can see that the acceleration is proportional to 1 over the radius. And why is that happening? Well, because when we increase the radius, we find that the change in velocity is unaffected, but the time taken for that change increases by that same amount, and therefore the acceleration decreases by that same amount, giving you the acceleration proportional to 1 over r. There we go, an intuitive explanation for why acceleration has a v square over r in it. In this video, we'll clarify all the confusions between centripetal and centrifugal forces.
sun. So the Earth is moving in a nearly circular path around.
The Poincaré conjecture. In 2000, the Clay Mathematics Institute, a non-profit organization, offered a $1 million prize for solving each of 7 important unsolved problems in mathematics. Poincaré conjecture, posed by Henri Poincaré around 1900, was one of these problems. Henri Poincaré was a famous French mathematician who lived around 100 years ago. He studied a special kind of math called topology. Topology is all about shapes and how they can be changed. For example, you can stretch or twist a shape, but you can't cut it or glue it together. Topologists want to find ways to tell different shapes apart, even if they look different but can be changed into each other. When it comes to 3D shapes like a ball or a donut, it's not too hard to figure out what they are. In a way, a ball is the simplest 3D shape of all. Poincaré wondered if the same thing is true for 4D shapes. He thought that maybe there is one 4D shape that is the simplest, just like how a ball is the simplest 3D shape. This idea ended up becoming known as a Poincaré conjecture. About 100 years after Poincaré came up with his idea, a Russian mathematician named Grigory Perelman found a way to prove it. In 2003, Perelman posted his proof on a website called Archive, which is where scientists share their work. Perelman's proof was really important and groundbreaking, but it also had a few small problems that needed to be fixed. Perelman's proof also used a lot of the work done by another mathematician, an American named Richard Hamilton. Even though Perelman's proof wasn't perfect, it was still a huge deal. He had finally solved the Poincaré conjecture, which had been a mystery for a very long time. He proved it using the Ricci-Flow method developed by Richard Hamilton, and Hamilton laid the foundations for using Ricci-Flow to attack the Poincaré conjecture. The Ricci flow is a set of partial differential equations that deform the manifold in a certain way. It usually deforms manifolds into round structures, but can sometimes encounter singularities. To handle singularities, Perelman introduced Ricci flow with surgery, in which he manually removes the singular points and replaces them with smooth structures.
Number one, it is always directed towards the center. And number two, it is perpendicular to the linear velocity of that object. Common examples of those forces are, for example, the tension. If you have something which is being rotated in a circle, it could also be the gravitational force, it could be the frictional force, etc. The formula for it is given by mv squared divided by r. Now, from that equation, we can entail that there is a centripetal acceleration which is towards the center of rotation, and that centripetal acceleration is given by the formula of v squared divided by r. Okay, next one. Now, in circular motion, the linear velocity changes, however, the linear speed is constant. How can this be? Remember, you can have acceleration as constant speed because velocity is a vector quantity, and only the magnitude, i.e. the speed, remains the same. However, the direction is constantly changing. So the centripetal acceleration changes the direction of motion only. Now, this next question is really important. That's why I put this in red. Why does the speed of an object in circular motion not change? Now, the reason for that is because the net force is directed perpendicular to the direction of motion, i.e. the velocity. Now, this means there is no work done by this force, and hence there is no change in the speed. Remember, work done in general is equal to the force times the displacement times the angle between them. So it's fx cos theta, and cos of 90 degrees is equal to 0, which means that the work done will be 0 if the force F and the displacement x are perpendicular to each other. Now, because v is equal to omega r, we can rewrite the following two equations, one for the centripetal force and one for the acceleration, as the following. F is going to equal m omega r squared divided by r, which is going to give us m omega squared r squared divided by r. We can cancel those out, which is going to give us m omega squared times r. Similarly, for the acceleration, this is exactly the same equation, just without the mass in front of it. This is going to equal to omega squared times r. Let's have a look at an experiment to try and investigate circular motion. So we have the following setup over here, in which we have a bunk which we're going to spin. That's connected on a piece of string that goes through a glass cylinder, and it reaches a mass on the other end. I'm going to try and keep the radius of the motion constant. We would normally try and do that with a marker we could have that we've placed on this end of the string, just where it meets the glass cylinder. And we're going to be varying the mass m. There are many different variations of this experiment, so something could come up in a question, which, for example, you are keeping the mass constant, but you're varying the radius r. So be prepared to be quite flexible in how we're going to approach this problem. We can measure the mass m with a top-hand balance, and then we could calculate the weight, which actually provides the centripetal force, and that weight is providing the centripetal force once again, which is equal to just mg. We're going to measure the radius r with a ruler, and then we're going to be timing 10, at least 10, I would say, 4 oscillations, 10 full time periods with a stop clock, and we're doing that to reduce the percentage uncertainty, improve the accuracy in our experiment. We're going to calculate t by dividing by 10. After that, we could calculate our velocity using v is equal to 2 pi r over t, and then we could calculate v squared for different values of m. In terms of our analysis, we're going to plot a graph of the force, which is just mg, against v squared. Now, if the formula for centripetal force is true, the graph will be a straight to our gradient, it's called grad, times r. Okay, now let's have a look at circular motion at an angle. So we have something like a car which is turning to the left. The normal reaction R is always at 90 degrees to the angle of the slope. So that means that this angle here is going to be equal to this angle here. This is because of similar triangles, by the way. And we can split the normal reaction R into two components, R cos theta and R sine theta. Now in this setup, R cos theta is going to be balancing out the weight because that's the vertical component acting upwards. So if the car is not moving up or down, this better be equal to the weight mg. And R sine theta, this component of the normal reaction, will actually be providing the centripetal force because that's the net force acting towards the direction of turning. So R sine theta is going to equal to mv squared divided by r. Very, very similar in a conical pendulum that is at an angle theta. The vertical component is the adjacent, which is equal to t cos theta, and that is equal to mg. Additionally, the horizontal component is the one component which is acting towards the center of rotation. That actually provides the centripetal force. So t sine theta is equal to mv squared over r. Circular motion at an angle could be represented in many different situations. For instance, you may have the lift force or some frictional force which is making something turn. So please be aware that tension and the normal reaction are not the only examples of forces in which this type of problem could be applied to. A typical problem would ask us to calculate the speed in this situation. If that's the case, we need to have a look at this system of two equations. The way we would normally do it is just rearrange one of the equations for one of the unknowns. For instance, t. We can say that t is going to equal to mg over cos theta. And then what I'm going to do is I'm going to input this equation into this expression over here. So rather than t sine theta, I'm going to write mg sine theta over cos theta is equal to mv squared divided by r. Notice that my other unknown, which is the mass in this case, is going to cancel out, and sine over cos is equal to tan. So I'm going to get that g tan of the angle is equal to v squared divided by r. In other words, v is going to equal to the square root of gr tan theta. Okay, and finally, let's have a look at vertical circular motion. So this is just an example of some washing which is spinning in the drum of a washing machine, but this could be a bunch of other situations as well. For example, it could be a mass on a string that is being moved in a vertical circle, or it could be a roller coaster in a loop on a plane doing a vertical loop, etc., etc. Now, let's imagine two positions, 1 and 2. Now, notice that in position 1, mg and the normal reaction R are in the same direction. Position 2, mg and R are in the opposite directions. Let's apply Newton's second law for each of those directions, each of those positions. So for position 1, ma is going to equal the sum of the two forces. Now, they're in the same direction, so I'm going to add them. So I'm going to say this is equal to mg plus r. Now, remember my acceleration in this case, because we're moving in a circle now, is centripetal. So this is going to equal to mv squared over r is going to equal to mg plus r. Now this means that in position 1, the normal contact force will be equal to mv squared over r minus mg. Now in position 2, we're going to follow exactly the same procedure. I'm going to write that mv squared over r is going to equal to, now we're going to have to take them away, and it will be r minus mg, because we can see that they are in the opposite direction. So just rearranging for r, once again, we're going to get that r will be equal to mv squared over r plus mg. Now notice that r will be the greatest in position 2 because we are adding those two quantities. Okay, folks, now this was most of the A-level specification on circular motion. Thank you very much for watching. If you've enjoyed this video, please consider subscribing. And please do remember that this is insufficient revision, and now it will be up to you to do every available past paper question on circular motion to really make sure that you understand this topic. Thank you very much for watching.